Today we are going to be looking at forces and moments as applied to orthodontic aligners, which is a topic that is not really well studied because all the biomechanics books and publications relate more to importance of the biomechanical concepts in fixed orthodontics, and aligners are different in their force application when related to orthodontic tooth movement. So our introduction will be to explain how to control and direct the moment to force ratios with aligners. Again, very important concept where you have a force and a moment applied to one tooth, and then also what happens when you apply the same concept to a group of teeth. And aligners again are completely different because you can stage, as you know, the deformation of the aligners to obtain the requested or required movement. In orthodontics, we use simple forces a lot. In aligner movements, those forces only translate to a push, meaning that when you have a tooth, you can push on it in all sorts of directions for intrusion, for crown movement, but you cannot really pull it up if you do not have specific attachments. So if you had an attachment, then you will be able to push on the tooth, which will be translated in orthodontic fixed appliances to a pull. So remember that there is no pull in aligner treatment, only push. Then the next idea of very important concept in orthodontics to get a correct tooth movement is you have to be able to apply moments, because as we all know, and obviously depending on the bone level, the center resistance will be at a certain position on the root, and we tend to apply, especially with aligners again, we tend to apply the force only at the crown level by putting pressure on the crown. Let's assume you're putting pressure on this surface right here. There'll be a force, a push, and this force will be at a distance, as we all know, from the center of resistance, distance D, and this distance will create a moment, which is a rotational movement. So the tooth will be, in this case, tipping, because you will have a force and a moment. So these two systems will create what is called by Dr. Burstone and others as the moment to force ratio. And depending on the proportions, you will get different types of tooth movement. So always keep in mind this, the moment to force ratio drives the type of movements you will want to obtain on a single tooth, but it also applies, by the way, to a group of teeth, because a group of teeth will have a different center resistance, so a different distance, which will translate into a different moment to force ratio, resulting in different types of tooth movement. So that's what we call also the line of action of the force. So depending where the line of action of the force will be applied to, case like this one, as an example again, assuming you would be able to apply a force to this poorly designed tooth, if you put a pressure point from your aligner at this level and you push, or you put a pressure point at this level and you push, the distance to the center resistance will be different, obviously, and your moment to force ratio will be different. because the line of action of this force is further away from the center resistance than this one. The longer the D, the more rotation you will get. So always keeping that in mind when you are programming your aligners and how they will be applying the forces, that it's super important to be able to try to manipulate where the moment or the force will be applied to get this moment to force ratio. In biomechanics, we look at the bracket all the time, and these have been published extensively by many great orthodontists, one being Dr. Burstone, Dr. Melson. All these people are really experts. And what happens is you will get a wire, and at a single tooth level, you can definitely calculate what the wire to bracket interface should be doing, because you have a fixed system and you can apply a simple force by deforming or pushing or using an elastic as an example. You could put an elastic here. So then you have a determinate force system, and if you know the distance to the center resistance, you should be able to calculate your moment to force ratio, in this case the AP dimension, or you can also calculate it in the buccolingual dimension in order to assess roughly what will happen to the tooth movement when this force F is applied. The problem is with aligners is they are not doing the same thing. They have what we call a controlled elastic deformation, and then depending on how you will be deforming the plastic, you will get vastly different force systems. So this force application, which has been described many times in orthodontic textbook, is still valid at the theoretical level, but at the clinical level it's much more complicated. The problem that we have again is the aligner setup is different from a bracket setup, so you cannot really calculate into the same biomechanical environment. What aligners have are shape. Obviously, you can change the shape of the aligner by changing the virtual staging of your malocclusion. You can vary the thickness. This is a bit more complicated. It involves nowadays the advent of shape memory polymers, which we will discuss eventually, which are the new 3D printed aligners, which will give us all new horizons of varying the thickness, and obviously the modulus of elasticity, which is E, very well known. We all know that in orthodontics. We've calculated this with all our wires. The E in this case has to do with the type of material that you will be using. They all have a different modulus of elasticity, and depending on what is needed, you may be able to use a different material to obtain the movement that you want. This one here is nowadays, this is the new concept that we are developing. Hopefully the companies using, we call Gen AI or generative AI. So then the software will be totally in tune with the materials we'll be using, unlike at the moment where we use pretty much always the same material, be it Invisalign, be it Zendura, be it many Essex material, whatever the brand. We tend to just use the software to stage the case and then apply the same type of materials for any type of tooth movement, which is not optimizing aligner orthodontic treatment. So these are called now, we call the SMPs, which is shape memory aligners, which is exactly this right here. You can see that, SMP. Are coming in, one is Graphy, one is Lux Creo, one is, I don't remember the name, Senatec, I think. So they are coming on the market in the past 5 years, and hopefully we'll get special software to take advantage of this new capacity. So the Hooke's law is super important between the stress and the strain. So it's called the stress-strain curve. So, well, you put a little curve like this, and you calculate the stress, which is usually called in conventional orthodontics force, and strain, which is in our world deformation, if you use wire as an example. And we know very well that every single material we use has a specific stress-strain curve. It could be completely linear, it could be this way. So many materials can be obeying the Hooke's law because all materials are not necessarily fully rigid, so they have elastic properties that are taken into advantage. The best example would be night-tie wires for fixed orthodontics, and obviously aligner materials for aligner orthodontics. So we're going to apply the stress, which will translate into a force per unit area, which becomes a pressure. Again, hard to calculate because you don't really see what's happening. This is the Young modulus of elasticity, which means the material's relative stiffness. Again, you can use SmartTrack, Zendura, Graphy, Lux Creo, so many different brands, Show from Germany, I think. So they all have this E attached to their characteristics, and depending on what you want, you can get a material that is stiffer or more elastic, that can be more deformed, and it will respond to the Hooke's law, equals the E right here times the deformation. So stress-strain curve, this is exactly this one here. So it is pretty proportional, and it will be proportional depending mainly on the characteristics of the material and the amount of deformation. All these have to be taken into account when you are preparing your staging for the aligner treatment. You create an aligner at stage 5, whatever it is, and then you create an activation, which is basically the activation is actually caused by the displacement of the tooth in space, in 3 planes of space. So this displacement will deform the material, as we all know. And then you can calculate it by this simple equation, which is theta is the force apply. And interestingly enough, this is the elastic deformation you get from the aligner, right? So this one is when you deform it, you push it, so the aligner has to go around the teeth, get deformed. There is some stress applied, which is actually directly proportional to the force applied, which is the strain we just looked at. This is interesting, the length. So there is an amount of distance between active parts of the aligner called the length. And depending on the length, you will get different deformation, which will translate into better activation, because you can see that the more distance you keep, let's say, between the attachments. So if you have attachments very close, where the elastic properties of the aligners cannot really be expressed because of the proximity of these attachments right here, you will get less movement or less deformation than if you have the same concept and you push the attachments at a different distance, and you will get better deformation. So that's something you need to keep in mind when you design your appliances. People tend to put a lot of attachments, thinking that it will help the movement, which is true in a sense, but it also has a problem by removing some of the potential deformation of the material, which reduces the potential of controlled tooth movement. This is inversely proportional. This is the cross-sectional, this is basically the thickness, or when you cut the aligner. See, that's the inverse proportion. The thicker the alignment, the less deformation you'll get. We all know that. The last property is the amount of elasticity you get from the Young modulus of elasticity done by every single aligner company. So that's the end of part one. I would just, in conclusion, make a point. There are many important aspects. One is the type of material you'll be using. Very important. Which is the modulus of elasticity. Remember that? You will have also the amount of strain, meaning how much you will deform the aligner between stages, from stage 1 to 2. How much? We usually always use, like 0.2 millimeters of translation and maybe 2 degrees of rotation. But that's an average. You should be able to, in some cases, decide what you want to do. You also need to calculate your amount of material in between the active part. So this would be the length, and also the thickness of the material plays a super important role. And when you can get all these into an equation, which is very difficult to calculate because it has to do with tooth anatomy and periodontal support, then you can optimize your software for every single case. So this is why we have so much variability in our aligner treatments, is at the moment the software and the aligner materials, and the fact that you may end up trying to apply forces that are not really optimized for the type of malocclusions you are correcting, is still getting us into sometimes unpredictable results. So this is the end of part one. Hopefully you enjoyed it. And I always, as usual, like to get comments and feedback and see how we can improve further this discussion. Thank you very much.